To know the magnitude of the force on a charge moving in a magnetic field, this is the expression what we have. See, F is equal to Q into V into B. B is the magnetic field strength or the magnetic induction B. Okay, V is the velocity of the charged particle and Q is the magnitude of the charge. We'll assume that the magnetic field is going in this direction into the board this way. So the crosses indicate that the direction of the magnetic field is going into the board. Okay, that means it is perpendicular to the plane of the board. Fine. Now I am taking a charged particle Q and I am forcing it to pass through the magnetic field of induction B. Okay. Now to know the magnitude is this much, Q into V into B. But to know the direction of the magnetic force on the charged particle moving in this magnetic field, we use the right hand rule. Okay. So we place our right hand in the direction of the velocity of the charged particles. And then we will curl our fingers in the direction of the magnetic field. Okay. You know that magnetic field is going into the board this way. So I am placing my right hand fingers, I am pointing my right hand fingers in the direction of velocity and curling those fingers in the direction of the magnetic field into the board this way. Okay. When I am facing this way, now the thumb is stretched like this in the upward direction. So this thumb is indicating the direction of the force. That means force is in the vertical upward direction. Imagine the situation is reverse. That means instead of going into the board, if at all I have the magnetic field coming out of the board. Generally what we denote by coming out of the board is a dot with a small circle around it. Because so each dot with circle is representing a magnetic field line. See, as similarly as here, each cross. Okay. So all these dots with surrounding small circles indicate that magnetic field is coming out of the board. So direction is perpendicular to the plane of the board but coming out of the board, that is opposite to the direction what we have discussed here. In this case, if at all I assume that a charge Q is going in the same direction with velocity V, I wanted to know the direction of the force. I use again the right hand rule. Okay. Now I point the right hand fingers in the direction of the velocity and now I should curl them in the direction of the magnetic field. Direction of the magnetic field is like this, coming out. So I cannot curl this way, I should curl this way. Okay, I should tilt my hand and then my fingers are in the direction of the velocity and I should curl them in the direction of the magnetic field. So they are coming out of the board. So this is the direction. So I should curl them in this direction. When I curl them in this direction, my thumb is pointing downwards. This downward direction will be the direction of the force on them. Always it is not necessary that the direction of the velocity and direction of the magnetic field both need to be perpendicular. Okay, in these two cases what we have discussed here is that both are perpendicular to each other. So one is the direction of the velocity of the charged particle, another is the direction of the magnetic field. So these two directions are perpendicular to each other here. It may be possible that there is some angle between the two. So magnetic field direction is this way, not exactly into the board, perpendicular to the board, but making some angle. Okay, but into the board like this. Okay. Then in that case, what should I consider the velocity? I should consider the component of the magnetic field in this direction. Okay, that will become B sin theta. So whatever the component of the magnetic field perpendicular to this V, we'll consider that. Then the magnitude of the force will become QVB sin theta. Here theta is the angle between the direction of the velocity of the charged particle and the direction of the magnetic field. So we don't have anything to do with Q over here. Okay. In case theta is equal to 90 degrees, then sin 90 degrees is equal to 1. That is what we have discussed the two cases earlier. In case the theta is 0, that means both are parallel. That means the magnetic field is coming out of the board over here. Velocity of the charged particle is also coming in the charged particle is also coming in the same direction. Okay, or else if the charged particle is going in the direction into the board, whereas the magnetic field is coming out of the board. In such a case, theta is equal to 180. If both are coming in the same direction, the angle between them is 0. If both are going in the opposite directions, that means the charged particle is coming out of the board, whereas the magnetic field is going into the board. In such a case, the theta angle is 180 degrees. For both the cases, sine 0 as well as sine 180 degrees, both are equal to 0. In such a case, then the force will become 0. Okay. So this indicates that whatever the force is there, the force between the direction of the velocity, when force on a charged particle going in a magnetic field is equivalent, is given by the expression F is equal to QVB sin theta, where theta is the direction between the direction of the velocity as well as direction of the magnetic field. Okay. Now, when we know the direction of the magnetic force on a charged charged particle when it is entering into a magnetic field, so let us see in what direction does it move and how does it affect its type of motion over there. What's happening is I am considering a magnetic field, uniform magnetic field. Crosses indicate the direction of the magnetic field into the board. I am having a charged particle Q, and I am throwing that into the magnetic field. The strength of the magnetic field is B, okay, in this direction. Now the force is QVB definitely, okay. Now in what direction does it move? To know the direction of the motion of the charged particle, we need to know the direction of the force. Initially it was thrown in the horizontal direction. Now we need to know the direction of the force. So according to the right hand rule, so we are facing all the fingers of the right hand in the direction of the velocity, and now curling them in the direction of the magnetic field. As they are into the board, so we'll curl them this way. When we curl them this way, the thumb is pointing in this direction, so the charged particle, the force is acting this way. So as soon as it is entering, a force acts in this direction of this magnitude. The directions between the velocity and the magnetic field both are perpendicular like this. So sin theta is equal to sin 90, that is 1. Okay. So there is no sin term written over there, that is the reason. Okay. Now when there is a force directed perpendicular to the direction of velocity, what happens? Does it continue to move this way? Definitely not. So it will try to change its path. Whenever it is trying to change, always the force is perpendicular to the velocity. So what will happen now? If the velocity is in this direction, again the force is appearing in this direction. So now because of this force, the velocity of the charged particle continuously changes. Whenever the velocity, magnitude is not changing, I am talking about direction. Direction of the velocity of the particle continuously changes. Because of this continuous change, it will not go in the straight path, it will follow a circular path. Okay. Now when it is going in a circular path, let us assume this is a circle. Okay, I am a bit poor in drawing. So let us say this is the center of the circular path. Now, and from this center I will take radius r. Whenever a charged particle is moving in a circular path, there is one type of force acting on it. We'll call it as a centripetal force. Centripetal means directed towards the center. Okay, directed towards the center. Centripetal, towards the center. So this force is always directed towards the center, because of which the charged particle is moving in a circular path. This centripetal force is given by the force on the charged particle because of the magnetic field. Okay, so the expression for the centripetal force is given by the expression mv square by r. V is the magnitude of the velocity with which it is rotating now, and r is the radius of the circular path. These two are equal. Now from equating these two, we will be able to calculate what will be the radius or what will be the velocity, like this. So let us assume that equating this to mv square by r is equal to q into v into b. I can cancel out this one, okay, and I'll be able to get what is the velocity for this, or r is equal to mv by qb. Okay, this is the radius of the circular path. I'll be able to calculate. Instead of that, if I wanted to calculate what is the velocity, okay, I'll be now it is going in a circular path, okay, radius is r. Now this is being a circular motion, it is a periodic motion. If I wanted to know what is its time period, okay, if it is making one complete rotation like this, then whatever the time it takes for one complete rotation, that will be taken as the time period. So how do we get the time period? It is nothing but the total distance traveled by the velocity, magnitude of the velocity. So total circumference is nothing but 2 pi r divided by velocity. Now I know what is r from this expression. I can substitute for r in this expression. So I will get this as t is equal to 2 pi by v into, instead of r I can write mv by qb. So which gives us 2 pi m by qb. So that means if I know the mass of the charged particle, if I know the strength of the magnetic field applied over there, then even without calculating what is the velocity of the charged particle, I will be able to calculate what is the time period of its rotation when it is going in a circular path. Okay, I will also be able to find out what is the radius of the circular path with which the charged particle is moving in a magnetic field. Okay, now we have seen a situation where a charged particle is moving in a magnetic field, an external magnetic field which is applied. We are considering it to be uniform. Okay, in case instead of a charged particle, we will consider a conductor which is